Okay, so let's take a look at the next problem, which is problem 5, and this was a proving question. All right, so I think we need to solve for the second order differential equation first. So it's y double prime plus n squared y equals to 0. So I'll write that as we have done in other problems, n squared equals to 0. So by subtracting by n squared both sides is what we have. And let's apply square roots. So we have r equals to plus minus. Negative 1 will come out as I, and square root of n squared is just n. So these are our two solutions, positive I and negative I times n. And since these are our complex solutions, we can, the third case from our, I guess, last week's homework can apply. And so we have our answer as phi of x equals to C1 cosine of nx plus C2 sine of nx. We would have e to the power of alpha x in the front, but as we know, this is 0, and our alpha value is 0. So let me just write the general format of complex solutions would be phi of x was e to the alpha x, C1 cosine beta x, plus C2 sine beta x. And this would be, this is a general solution set for r equals to alpha plus minus beta I. Okay, so that's what we have, and let's take a step back, and we know that this is in the form of phi of x equals to C1 phi 1x plus C2 phi 2x. This was from the chapter reading, so we understand that phi 1 of x, this is equals to cosine of nx, and phi 2 of x, this equals to sine of nx. Okay, so now let's determine if this is linearly independent or dependent. I think testing that out would give us a lot of additional information. So we're going to apply the Wronskian. So we know from the textbook reading 1 comma phi 2, this is going to be equal to phi 1 phi 2 prime minus phi 1 phi 2 1 prime. And if this is not equal to 0, then that's going to be linearly independent. So let's check. So our phi 1 is just cosine of nx. Phi 2 differentiated, that's going to be n, and cosine of nx, so that's going to have the square. We have the minus. Phi 1 squared is n times negative sine, so negative and negative become positive, so we have the sine of nx, and we have to multiply that by phi 2, which is the sine of nx squared. Okay, so we can take out the n, and that would give us cosine of nx plus sine squared of nx. And from our rule of algebra or pre-calculus, we know that that's cosine squared plus sine squared, that's going to equal to 1, which gives us just the value of n. And the n is given 0, 1, 2, and so on. So we're looking at the two cases here. If n is 0, then this equation would be linearly dependent. But if n is not equal to 0, then we're looking at the linearly independent solution set. Okay, so the next thing that we're going to do is we're going to actually utilize the hint given and see if we can go from there. Okay, so we're given that negative phi of n double prime, this is n squared phi of n, and we're also given negative double prime of m is going to be m squared of phi m. And this is true if you try differentiating twice of phi 1x and phi 2x, we will get to this result. All right, then what I'm going to do is I'm going to multiply phi m and phi m, and to the second equation I'm going to multiply phi of n. All right, so from here now what I'm going to do is, if I take a look at this equation, I'm looking at something like n squared minus m squared. So if I go back, I'm gonna subtract the second equation from the first equation. So let me just rewrite the second equation just right underneath the first one. So we have phi m double prime phi of n equals 2 and m squared phi of m phi of n. All right, so now what I'm going to do is I'm going to subtract these two equations. Okay, so on the left hand side I have phi double prime m phi n minus phi double prime n phi of m. So this equals to n squared minus m squared and phi n phi m. All right, so this is getting similar to what we're given. I think we were able to get here, and we know that the left-hand side of our equation, so left-hand side, this is the same thing as phi of n phi m prime minus phi m phi n prime. Okay. Alright, so now what we're going to do is I'm going to differentiate both sides from 0 to 2 pi, because those are our boundaries given, of dx and dx. Alright, so I'm going to work from the right-hand side. So the right-hand side, this will become, this differentiated sign, and the integral will cancel out. So we have phi n phi m prime minus phi of m phi of n prime. That's going to equal to, this part is just that's the constant, so I can take that in front of our integral. So we have phi of n phi of m dx 0 to 2 pi. Our main question, what we're trying to prove is this one, this part, which is identical to what we have right here. We just need to divide both sides by n squared minus m squared. So let's divide, so that's going to be gone, and we have n squared minus m squared. And we can divide both sides by n squared minus m squared because of the given fact that n is not identical to m. So we know that that's never going to be 0. So we are safe to divide. Okay, so now if you take a look, this is the boundary problem. If we utilize the boundaries given, so we know that 0 and 2 pi are going to be the same, and the ones differentiated about the boundaries are going to be the same. So what that means is this and that, phi of n to the first of 0, and this is 2 pi, those two values are going to be the same, and the one with the black underline, those two are going to be the same because the boundary of 0 and 2 pi are going to be are equal. So therefore, we have this whole thing, the numerator part equals to 0, and 0 divided by any number or any non-zero number is going to be equals to 0. So we have proved that this phi of n, phi of m differentiated or integral of that between 0 to 2 pi equals to 0. Alright, so showing the part B is easier. The part A was the proving, which was the harder part. Now that we have proved that this is true given the boundaries, given such boundaries, as long as the boundaries are sufficient, we know that they are going to equal to 0. And the functions with the trig functions is that the value, especially with the cosine and sine, because they have the frequency of 2 pi, we know that cosine of 0 is going to be the same thing as cosine of 2 pi. Likewise, the sine of 0 is going to have the same value as sine of 2 pi. So therefore, any mix of cosine and sines are going to be equals to 0. That's not true for tangent. If we can prove that, if we had and proved that y of 0 equals to y of pi, because tangent value, it repeats at the interval of pi, then this would be true. But for our given boundaries of 0 and 2 pi, all of these are going to be equal to 0. Alright, so number 6 is a developmental problem that ultimately reaches part B and C, but I only assigned A. So let's go ahead and solve this. So this is a second order differential equation, so I can write this as n squared plus r squared plus n squared equals to 0. Actually, let's even before that, we know that this is one of the solution sets. So let's just go back what we did. I think during the first 3 weeks, when we were first introduced the first order and also the second order differential equations, we can just immediately find the y double prime and plug that in accordingly. So let me scratch this out. Alright, so phi of n prime of x, this is going to be n cosine of nx, and phi double prime of n of x, this is going to be negative n squared sine of nx. By plugging in this into y double prime and plugging in the sine of nx into y, we get n squared sine of nx plus n squared sine of nx equals to 0. So this is satisfied, but we just got to make sure our boundaries work. So for when x is 0, then we have sine of 0, that's going to equal to 0. So the first boundary value is satisfied. The second boundary problem, if x is pi, then n takes values, all the positive counting numbers. So we have the sine of n pi, that's also going to be 0. So the second boundary problem is also satisfied. So this is a quick way of showing, I think probably the easiest way, just finding the derivatives and plugging it accordingly, and showing that this equals to 0.